You remember high school algebra, right? All that time spent solving for x, rearranging equations. It probably felt pretty abstract back then. Well, it turns out that exact same math is the secret language humming away inside every single electronic device you own. So let's dive in and really uncover this hidden link between a subject you took in school and the smartphone that's probably in your hand right now.
I know, it sounds like a huge leap, doesn't it? How can these simple-looking equations possibly have anything to do with something as mind-bogglingly complex as a computer chip? That's the big question we're going to unpack. We're going to see just how engineers go from these basic formulas to commanding the billions of transistors that literally power our modern world.
Okay, so before we can even begin to tackle the complexity of a microchip, we've got to start with the absolute basics. And the fundamental truth is this: at their very core, the rules that make simple electronic circuits work are, believe it or not, just pure, straightforward high school algebra.
Take this for example. This little guy is a super common component called an operational amplifier, or an op-amp. You can kind of think of it like a volume knob for an electrical signal. Its whole job is to make a signal stronger. And the formula that tells you exactly how much stronger? It's this beautifully simple algebraic equation. No calculus, no quantum physics, just variables you can solve for, exactly like you did back in math class.
And here's where it gets super practical. Let's say an engineer knows exactly how much amplification they need, and they know the value of one of the resistors. Well, to figure out what the second resistor needs to be, they do exactly what we all did in ninth grade. You just isolate the variable. They shuffle the formula around, plug in the numbers they know, and boom, they've just designed a critical piece of their circuit.
And this is really the key. For these basic building blocks of all electronics, the math really is, as this engineering worksheet says, nothing more than an exercise in algebraic manipulation. It's refreshingly simple. But what happens when you don't just have one of these circuits, but thousands of them, all linked together?
And this is where our story takes a sharp turn. Because, the circuits in our devices aren't made of 3 or 4 little parts. We're talking millions, sometimes billions of components all interacting with each other at the same time.
So, have a look here. On the left, you've got a simple circuit, the kind of thing you'd solve in a textbook. No sweat. But on the right, that's a little closer to reality. See, every single loop, every connection point, it adds a whole new equation to the pile. And honestly, this is still incredibly simple compared to what's inside a real microchip.
All of a sudden, you're not just solving one equation. You're trying to solve hundreds, maybe thousands of them, and they're all connected. As one student paper on this subject put it, trying to do this by hand quickly becomes, well, very time-consuming and tedious. It's an absolute logistical nightmare. I mean, just look at this mess. This is what happens when you try to solve a big system of equations by just substituting one into the other. You solve for one variable and you get this huge, ugly expression. Then you have to plug that into the next equation, which just gets even messier, and on it goes. It's a total explosion of numbers and variables. It is quite literally like trying to untangle a giant ball of yarn in the dark. There has to be a better way, right?
And thankfully, there is. The hero of our story isn't a person. It's a mathematical tool that feels like it was born to solve this exact problem. And that hero is the matrix.
And this just shows the difference so perfectly. On the left, you have that chaotic, tangled mess of substitution. But on the right, you have the exact same problem, just represented as a matrix. Look how clean that is. It's just a grid of the important numbers, the coefficients, all neatly organized. All the relationships between the variables are still there, but all the clutter? It's just gone. This amazing technique of arranging equations into a matrix and then just following a simple step-by-step process to solve them has a name. It's called Gaussian elimination. It's like having a recipe that turns the messy art of algebra into a systematic, repeatable science.
So here's the crucial point. Humans look at a matrix and think, oh, that's organized. But computers absolutely thrive on this stuff. A computer can perform the simple, repetitive steps of that recipe on a massive matrix, millions of times faster than any human ever could. This organized grid is the perfect food for a computer.
Now, this brilliant solution, it's not just some clever party trick. It's actually part of a really deep and powerful branch of mathematics that was being developed decades ago, specifically to handle this kind of complex, systems-level thinking. Let's peel back the history a bit. So this right here, this is the title page of a foundational textbook from MIT. And look at the date. It was published all the way back in 1960. Even then, brilliant engineers and mathematicians knew that to really analyze complex systems, they were going to need a totally new kind of language.
And that new language was matrix algebra. It came with this whole new set of rules for how you could add, subtract, and multiply these grids of numbers. See, this wasn't just a way to organize equations anymore. It was a complete framework for understanding how all the different parts of a complex system influence each other. And this new way of thinking also gave us other incredible tools, like these things called signal flow graphs. What they let engineers do, basically, was draw a flowchart of the math itself, turning a page full of abstract equations into a visual map that they could actually look at and intuitively understand. Okay, so let's bring this all home. We've gone on this journey from a simple formula on a chalkboard to this huge interconnected problem, and then finally to this elegant mathematical system that brings order to all that chaos. The real magic, though, is how this completely abstract journey lands squarely in the palm of your hand.
Really, it's a story in 3 acts. First, you have these brilliant minds laying the theoretical groundwork decades ago. Second, the Matrix gave us the perfect tool to organize what seemed like impossible complexity. And third, modern computers gave us the raw horsepower to solve these huge matrix problems in the blink of an eye. And the result of that powerful combination, it's the seamless technology we use every single day. And here's the biggest takeaway of all. This branch of math, linear algebra, it's so powerful, it doesn't just design computer chips. It's the same math that's used to model quantum physics, to create stunning computer graphics, even to train artificial intelligence. In fact, every time you tap or swipe or talk to your phone, you are kicking off a cascade of commands that are, at their very heart, just a massive system of linear equations being solved in real time. So the next time you pick up your phone, just take a second and remember that invisible structure that's humming right underneath the glass. It's not magic. It's an elegant mathematical order. It's the ghost of your old algebra class, all grown up and running the entire modern world. The only question is, now that you know it's there, can you feel it at your fingertips?